Yeah.
Sorry for the technical problems.
No problem.
Please,
So,
go ahead.
hello everyone. My name is Todorov, and I'm here to talk about my work on the model mu calculus for free in Agda. But before we get to the exact work, let's first get some background and motivation. I think we can all agree that verifying large systems is hard. And in particular, let's consider an example. Let's say we have a cyber-physical system that has multiple communicating processes. Such systems are very common, usually, in the real world. However, they have a lot of risks involved in developing and maintaining them. For example, such systems are very error-prone because of the multiple interacting components, and they could be very expensive if they fail. And it is exactly because of the second fact that we usually want to make sure they don't fail. And we do that by verifying them. So this gets us to the question of how do we actually verify software, and how do we verify software systems? Well, there's usually three steps involved, three main steps. The first one is to define some mathematical model of our software. The second one is to express whatever functional requirements it should satisfy as properties of that model. And finally, we need to prove them either in a proof assistant or using some automated techniques such as model checking, for example. And this is where the model mu calculus comes in. The model mu calculus is a fixed point dynamic logic which has previously been widely used to reason about the behaviors of label transition systems. And the reason why is that label transition systems represent, well, sequences of operations that can occur in a program, and that is exactly what the model mu calculus reasons about. Possible sequences of operations in a program. For example, let's consider a particular cyber-physical system, an ATM, but a very simple one that only has one feature, allowing its user to view their bank account balance. If we wanted to model that as a label transition system, it would probably look something like that. It starts in a given state, its initial state, it gets some PIN code, it checks if that's correct. If it is, it shows the user's account balance, and let's assume if it's an incorrect, it just throws an exception, it holds. It could also go back to the initial state. And for such label transition systems, we can write properties using the model mu calculus, and they look something like this. So the property on the, well, it's my right for you left, says that in the initial state, it is possible to execute the get pin operation. And more concretely, it says that the first operation in the program is get pin, and there exists a continuation after that get pin operation for which the formula true holds. And the formula true is trivially satisfied by all programs. The formula on your right says that the show balance operation cannot be executed in the initial state. And in particular, it says that if the first operation was show balance, then the formula false must hold for all possible continuations of the program. And since the formula false can never hold, we can conclude that the first operation should not be show balance. However, neither of these properties are really exciting. We would like to be able to represent far more complex requirements. And the model mu calculus has the capabilities for that. Let's see some more interesting examples. For example, this is how we would express the liveness property using the model mu calculus. And the liveness property states that a program can never terminate. So the way that this is represented using the model mu calculus is, it says, well, that's the star we use to say that in any reachable state, there is some operation, and for at least one continuation of that operation, the formula true holds. And this formula looks admittedly a bit strange, and that's because there's a lot of truths in it, but they don't all mean the same thing. The last true is the formula true. All the other truths are so-called action formulas, which represents sets of operations, and in this case, they represent that any operation that is possible can be executed there. So it says, for any sequence of operations that we can execute, there's at least one more operation that I can execute for which the formula true then will hold. And we can also express safety properties using the model mu calculus, and this admittedly scary example is one such property. This is a property that is very valuable for an ATM, and it says that I cannot execute the show balance operation for a given user before executing the get pin for that user. And the way we express this in the model mu calculus, as we can see here, we use the greatest fixed point operator, which is a symbol in the beginning, and we name the fixed point x, and we give it a parameter of type bool. This Boolean parameter we use to signify whether the get pin operation has been executed for the current user, and that's why it has an initial value of false. Then the body of the fixed point says that if we execute any operation that is not get pin or show balance, that is inconsequential to the value of b, if we execute get pin, then we must be in a state in which get pin has not already been executed for that user. So that's what the not b does there. And it then gets us to a state in which get pin has been executed for the current user. And for show balance, we have to always execute it in a state in which get pin has already been executed. And it gets us to a state where it hasn't, because now we're talking about the next user of the ATM. So these properties serve as an example here of what we can actually do using the model mu calculus. However, there is a little problem with the whole thing that I've been talking about so far. And that is, does the model correctly represent the given software? Because those properties that I just stated talk about the label transition system that is supposed to represent my ATM. But does the ATM that I have, does the label transition system that I have really represent that ATM? And that has to be verified separately, because if we don't know and if we're not sure that it does, then the whole verification process could be useless. So we propose a solution to that problem by modeling software using the coinductive free monad in a proof assistant, in this case in particular Agda. And then we adapt the model mu calculus to using the coinductive free monad instead of label transition systems. So let's talk a little bit about the free monad and why we decided to use that. So the free monad is a data structure that represents arbitrary sequential effectful programs that use algebraic effects, and it is typically defined like this. However, this definition is not accepted by Agda because it is not strictly positive, namely because the functor f is not guaranteed to be strictly positive. So we need some way of representing strictly positive functors, and for that we use a standard approach, which is containers. So this is our actual definition of the inductive free monad. However, this data structure also has a problem, namely that it is limited to representing only finite programs, and we would want to reason about any program. And for that we need the co-inductive version of the free monad. To do that, we would theoretically want a data type that has the same structure as the data type free here, but it is co-inductive. Unfortunately, Agda does not support co-inductive data types, only co-inductive records. So we need to do a little trick to define the co-inductive free monad. And the first part of that trick is to define this type, which looks long and complicated, but it is actually the same data type free from the previous slide with one slight change. It accepts an f as a parameter, and then in the impure constructor, it calls that parameter f instead of itself recursively. So using this parameter f, we can actually embed this structure of pure and impure computations into either an inductive or a co-inductive context, depending on what we need. And this is the records that we get. Here, the int free record is completely isomorphic to the data type free from the previous slide, and the record co-free is the record for the co-inductive free monad which we need. So from now on, we're going to use the co-inductive free monad as our representation of programs. So we'll just put this alias to use. And the question now that arises is why? Why use the free monad for this? Why not some other representation of programs? And the reason for that is that, as I said earlier, the model mu calculus can be used to reason about sequences of operations within a program, and the free monad represents programs precisely as a sequence of impure operations that ends with some pure result. So it is a very intuitive match between the two and the way that they represent and reason about things. So let's see how this works in practice. Let's go back to our ATM example and see how we can define that using the co-inductive free monad. The first part would be to define the effect that the ATM will use. And this is how that looks in Agda. First we define the shape of the effect, which is essentially the set of operations that will be used. And then we define the effect itself as a container by giving it the shape that we've already defined. And then we give the position for each shape, which is the type of the continuation for each of the operations. We can then use that effect to define the following program, which is the precise implementation of the ATM that we saw earlier as a label transition system. We can see here that we do a get pin, after which we do a correct pin, and depending on the result of the correct pin, we either show the balance and return back, or we throw an exception and hold. So this is the representation of programs that we're going to be using in the framework that we have. And now let's see how we can use the model mu calculus to reason about such programs. So this is the code, and these are the three properties that we have already seen. In our framework, this is how we would express the property that the get pin is possible to be executed in the initial state. So the first operation is get pin. As we can see, there is a very clear similarity in the syntax between the actual definition and the one in the framework. We just need a little bit more constructors in our definition in order to account for the necessary additional data types. And the one for show balance being impossible, also very similar to the original. Now, when we get to the more complicated properties, well, we would expect that maybe the formulas get more complicated, but they don't. They still very much match the syntax of the initial formula. Again, the only additional things are the ACT-F constructors that say that this is an action. This is how we distinguish between the formula true and the action formula true. This is, to me, this is a more clear definition than the other one, but to each their own. And finally, the most complex property is this one. And that can be expressed in our framework as follows. And again, this looks a little bit scary and long and complicated, but so did the initial property, so no problem there. The only difference between our definition and the original one is that we don't use named variables. That's why we don't have the explicit name x for the fixed point operator. We instead represent them using the Brun indices. So that's why we have the ref zeros. Those would be references to the fixed point operator. And the other difference that there is here is that the initial value false that we give to our Boolean parameter is passed all the way here at the end of the formula rather than right next to the definition. Everything else very closely resembles the original syntax of the formula. And from these examples, although they are very limited, we can sort of get an intuition that the framework that we have allows us to, first off, embed programs in Agda in this definition using the coinductive free monad, a very similar style to the one of label transition systems. And then it allows us to reason about those programs using the model mu calculus without introducing too much additional complexity compared to the syntax that one would write on paper for those formulas. However, there's definitely more work to be done here, and there's many different directions in which one could take this work. So first off, and that's work that is still ongoing, one would ask, is the semantics of the model mu calculus that we have provided actually correct? And for that, we have to prove some meta-theoretical properties that should hold for the model mu calculus, and that is what we're in the process of doing. We have actually proven the properties for Hennessy-Muller logic, which is a smaller subset of the model mu calculus. However, for the full version of the model mu calculus, we need a change in some of the encodings that we use, and that's why it's still ongoing work. Additionally, it would be very valuable to perform a case study to see how this framework performs on real-world systems, because when reasoning about real-world systems using the free monad, using the model mu calculus, sorry, mainly model checkers have been used. That has not been done in a proof assistant, so it would be good to see how that would work in real life. Then adding support for concurrent programs, because currently the framework is limited to only reasoning about sequential programs. And finally, a very interesting direction in which this can go is we could try to embed a formula or a set of formulas into the type of the program, which would then allow us, hopefully, to define correct by construction programs, because we would need to give the proofs that the formulas are satisfied as we define the program itself. This is somewhat related to this work, but it's a very interesting direction in which one could go. Finally, I should say that for more details about the implementation, please look at our paper. Also for the proofs of all the properties that I have shown here, they're also given in the paper. Spoiler alert, they're kind of simple. They don't use any complex constructions, so that's great. And the full implementation is available on GitHub, So feel free to take a look and see what it's possible to be done with the framework. Thank you.
Thank you. We have time for a couple of questions. Please go ahead. Otherwise, I also have a question. So you started out with the motivation, well, we want to model these label transition systems.
Yep.
So how does this approach compare to like a more direct approach of defining label transition systems and then defining their semantics in some way in Agda?
Yeah.
Presumably you could also do that. What do you think are the advantages of this approach?
Okay, so the main advantage of this approach, and actually the way in which we solved the original problem that I stated, is label transition systems are models of programs that are definitely separated from whatever executable program that I have. While when using the model mu calculus with algebraic effects, we could generate runnable code directly from the model mu calculus model. And if we use effect handlers in order to do that, effect handlers that do not change the order of operations in the program, we know that the properties that we have satisfied using the model mu calculus will also hold for our runnable program. And this is a guarantee that we don't get using label transition systems.
Thank you.
I was actually going to ask something similar to that. So since this is a monad, so you can't really statically extract the whole description of the process. Like you can run it in different interpretations, but you can't really get a global view. So isn't that going to be a problem if you want to move on to actually extracting the whole program from the description?
I'm not sure I exactly understand, but well, in order to extract or to derive the actual runnable program, you would just apply an effect handler that would give the implementations of all the operations that we list. And as long as it doesn't do any weird manipulations to the continuation, but it simply substitutes every operation with its actual body, then the order of operations which we have reasoned about using the model mu calculus should still be the same. So our properties should still hold, and we should have a runnable program because we don't have any more abstract effect operations.
Right, it will be runnable, but it will be in Agda. I mean, you can't, like if it's a monad, then because you have the power of the Agda function arrow at every branch, you can run it, but how would you get a global view of all the, like,
of all the
of the full behavior of the program? Like if you wanted to translate, like you can't write, I don't think you can write an effect handler or like an implementation of the effects in your framework that would statically, instead of doing something, would give you some finite description of your program because it's a monad.
Well, I'm still not entirely sure that I understand the question, sorry. This is the kind of description that you would get in the monad, right?
Yes.
And this is not supposed to be runnable. However, after you handle the effect here, in this case, you would get some program that does not have any effectful operations. It will just be a sequence of actually executable code, which will give some value at the end. So you could
yeah, but it will be
define an interpreter for those commands in some way. For example, that would actually execute them and give you a final result.
Do you have a slide on the satisfaction relation? Because that tells you the semantics of the formulas is such that the logical interpretation of the formula just inspects the branch structure of the Agda function.
I don't, because I have to be on Windows in order for the HDMI cable to work. I can get back to that after the presentation. I can switch back to my Linux. Yeah.
Okay, sure.
Okay. Well, then let's thank the speaker again.